Okay, thank you for the interaction. As said, my name is Michał and I live in Sweden, though I come from Poland. I come from Tri-City in Poland, Trójmiasto. Pozdrawiam ludzi z Polski. A couple of years ago, I moved to Sweden to join that company, 1337, which in English literally means 1337. So yeah, if you get the joke, you get it. We're a consulting company helping, like we started mostly as a .NET shop, but now we do all kind of stuff, and we're basically helping customers with more advanced problems. And today I'm going to talk about ML.NET, which is a machine learning framework for .NET. But let's start a bit with like general topic of machine learning and AI and like what's the difference? Because when you look at the media, how they describe AI, it's usually like this. It's this kind of unknown technology that's gonna came here to get us and kill us. But reality looks more like this. And it's much less fancy and a bit more down to earth. There is this joke written by Matt Velosa on Twitter that if it's written in Python, it's probably machine learning. If it's written in PowerPoint, it's probably AI. And it's a good joking way to like maybe show what are the difference between those terms. And if you want to be a bit more serious, I said a bit like that AI is like very wide topic and machine learning is some part of it. And if you want to be more specific, the most of machine learning we do these days is deep learning, which is like using deep neural networks. If you look like definition, artificial intelligence, it's a bit more wide and less defined concept. That basically it's like a form of intelligence demonstrated by machines that kind of reminds the human intelligence, so like learning and problem solving. And I personally feel that AI is this kind of like rabbit we're chasing, but we'll never get there. Like in the 1940s, this was considered machine learning. This is ENIAC, one of the first computers. It was designed to calculate ballistic tables for US Navy artillery. This is something that our phones can do now. And we don't really consider like calculating advanced trigonometry artificial intelligence anymore. But back then it was considered artificial intelligence. In the 90s, solving like the chess problem and playing chess was considered artificial intelligence. And computers are pretty well at chess right now. A few years ago, we broke another kind of barrier and playing Go. And now when we kind of understand more and more how deep learning algorithms work, we kind of consider it less of AI and more kind of just algorithms. And I think it's just how the progression works. When we stopped seeing the tech magical, it stopped being artificial intelligence. We just know better what it is, how we feel. And machine learning is like much well-defined than AI. It's like the scientific study of algorithms and using kind of computers to find patterns in data and then apply those patterns to newly seen data. So let's go through like a few type of kind of algorithms that used in machine learning. And one of the like most well-developed areas of machine learning is supervised learning. So we kind of supervise that learning with data that's been labeled, and we basically provide to the algorithm input and the right answers, and based on that, algorithm learns how it works. So the classic way of programming is like you take input data, you'll write some algorithm, and it will spit out the output. The way you like build algorithms with supervised learning, you take the input and output data and feed it into like the training algorithm, the training kind of pipeline, and you get the algorithm out. So basically a way to transfer the input to the output data. And then you use that algorithm to apply this data on to apply this algorithm to the new data. So we have basically two parts in the machine learning. Is a training part of training your algorithm, and there's using the algorithm to make some predictions, or and it's called inference. And one of the most common problems in supervised learning is regression. So basically providing one number based on some input data. And the classic example of regression is predicting a price of an apartment based off some input features. Like if you want to do based on one feature, it's going to be, for example, area of the apartment. It kind of makes sense. It's very logical because the prices of apartments are usually shown in the some amount of money per square meter. So it's usually like a linear, some kind of linear relationship, or maybe less linear, like I drawn here. Another common issue solved in supervised learning is classification. We classify a set of objects into like few things, for example, into few groups, for example, like expensive and not expensive apartments, or spam mail or not spam mail, or yeah, something like that. Or is it a cat on the image or a dog? The whole other and more, like much more interesting area of machine learning is unsupervised learning, because it doesn't require labeled data. Labeling data is very like work intensive area. To train those algorithms, you have to prepare a lot of data that's like labeled by humans, and it's very expensive. So there's a lot of like development right now in the more kind of unsupervised learning area, where you don't really feed the data and try to figure out things without those labels. There's like a lot of interesting development that I'm not gonna talk about out of scope, but like one of the classic examples of unsupervised learning is clusterization. So kind of finding groups of common objects or data points in your data set. So like finding some similar apartments, or finding customers that do similar things and can be like sold similar products and things like that. So just to have some grips how machine learning works in general, let's take a linear regression and see how it works. So we build that intuition. I showed this graph previously. If you ever did math, you know that there are some like input parameters on the horizontal axis. Those are parameters, input data, or features, whatever you want to call it. And we have some values. So for that kind of input value, we get that output value. And we can put points on that data set, on this kind of visualization. We can draw a line, which is basically like infinite amount of points that fit some function. And we can describe those functions with like basically two letters, two input parameters, A and B. A is responsible for the angle at which this function is going, and B is responsible for where we start, basically. So let's say we live in a world that the older you get, the more money you have, because you like do regular saving or something like that. And if we use examples with like A = 1, like with every year you accumulate like 1,000 of some kind of currency. In second example, if the A was bigger than 1, you accumulate those things much quicker. For example, you have higher salary, or are able to accumulate more savings. And the third example, when we have B bigger than 0, you can see that you start in a much better situation than 0. So you maybe were born to a rich family or something like that. And that's like basically like the mathematical description of linear function, a times x plus b. In the data science, we use w x plus b, just mostly because it makes sense for the naming conventions, because w's are weights and b are bias. So basically kind of looking into, for example, apartment example, w will be like the price for a square meter, and b will be all the kind of information that's not covered by this relationship. So, you know, when you buy apartment, the square meter is not the only information. You have actually much more information, like where's the location, how far away you have to the train station, things like that. And because in model we cannot cover all that information in our features, you always have kind of like a bias information. It's like information that's not completely included in the model. So let's look at this linear regression to try to predict how much you're going to pay for the taxi. It's like another example, classic of using linear regression, because it's also simple payment model. You usually pay for some amount of kilometers covered or time spent in the taxi, or both. So we start by looking at our data sets, and you know we kind of try to figure out, okay, let's draw some straight line. Just start linear function with like some random input parameters. Then in next step, we check how far off we are from this kind of our starting functions from our data set. And we calculate error function or cost function, which is basically like our measure of how far off we're from the best model. And cost function, like the simplest one used is square mean square error. Looks like that in the math version. And some people, when they start seeing those mathematical symbols, get scary. But you know, that sigma thing is just a for loop looking for us programmers. And basically for every point on this data set, we calculate square distance from the line and average over this. And this gives us some kind of metrics of how far away we're from the best solution. And now we're going to try to minimize it. And one of the common algorithms to minimize it is called gradient descent. So basically, if we chart A and B, for some values of A and B, this cost will be really high, and for some will be really low. And we're going to be trying to kind of make the steps to find the minimum of that function. So basically, we're going to go down that bowl to find that value. And if everything's go well, we're going to get something like that, which is going to be a model that will approximate the data pretty well. It's not perfect. It's very rarely going to be perfect. Actually, probably never, because data is never perfect. And this will allow us to make some predictions. So if you have a new data point, let's say 20 miles, then we're going to pay 450. That's probably, that's how the cost, for example, in Sweden, 450 kronor for 20 kilometers, something like that. And we have prediction model. Of course, this is like very simple example. You can do this math in your head, and especially that's only one feature. Then you can have much more features. You have time and so on, and this getting more complicated. You would need much more dimension to visualize it, and it's really getting hard for our brains. But math will take everything. Will take infinite amount of dimensions, and we can just do it in arrays, and that's okay. But it's getting really hard to visualize those things. So after that intro, let's look at ML.NET. So ML.NET is still relatively new product from from Microsoft. They introduced it in around 2019. It's a very high-level API. It's designed from this perspective, not kind of what algorithms you want to use, but from what algorithms you want to solve. So for example, you want to do regression. So that's where you start, and then you kind of dig deeper into problem. So a code first approach, you basically just, write everything in code, no drag and drop stuff like in previous Azure and Microsoft approaches. Microsoft claimed that they use this technology internally for years in products like Bing or Excel and so on. There's like no way to confirm that claim, but that's what's in official release materials. It's free, it's open source, cross platforms, works very well on Mac, works really well on Linux. It's basically written in .NET Core and have all the benefits of that environment. It was announced in May 2010, released in 2019, and currently it's at version 1.5. It's production ready, it has a decent set of features. I think the biggest drawback is it doesn't support usage of neural networks directly. You can import models that were converted into ONNX standard, or in some cases pre-trained TensorFlow models. It works really well in some cases, and not so good in some other cases. But in this area they're developing pretty heavily right now, and it's good to see. So the working plan is basically very similar to what we described. We first the build model, we're gonna train it, and then we're gonna infer from this. And you have this kind of data pipeline concept where you can in one stream of functions that you can chain, you can collect data, add different kind of elements of pipeline that will convert features, do some operation on features, normalize them. Then you train the model and you can evaluate it, get some metrics, and try to maybe rework that model. Or if you're happy with that model, you can save this model either to memory and use straight away, or save to database, or save to file and use in some other project, or use within the same project you just loaded into the memory. In most cases here, I'm gonna show that just straight away load into the memory and reused. But in more practical examples, you probably will have some kind of backend service running that will, for example, retrain on new data every week and just post this model into some kind of database. The way I work with clients, we usually put it in some sort of CI/CD system. So it's like working just every week, for example, weekend retraining the data, so it's going to be used freshly. And then we have that model saved or load in the memory. You can just create prediction engine and use that to build predictions. Or yeah. And if you look at code, those steps are kind of matching to. That's basically the simplest way to do a model. You create ML context, which is object similar to like a database context in entity framework. You're gonna pass it around a lot during the whole process. You load data from some kind of source. It has a lot of data loaders. You can load from database, CSV files, text files, JSON files, and so on. There's a lot of ways to ingest data. We build your kind of estimator, which is kind of training pipeline. So you can see we kind of do some featureization text. We add a binary classification algorithm, and that's all. And the fourth step, we kind of training the model, and in fifth we make a prediction. And that's basically like the simplest probably algorithm you can build using ML.NET. So yeah, let's get to the sample we talked with linear regression and do it in code. And the most code I'm going to show comes from this repository in GitHub. This is the official machine learning ML.NET samples repository, and they put a lot of samples for different algorithms, how to use them practically. It's very useful to kind of get a grip how to use the ML.NET apart from the documentation. And this is the input data we're going to use for the taxi prediction. We have some different features, like, for example, what was the vendor, what kind of rate they used, number of passengers, time of the trip, distance of the trip, if it was paid with cash or card, and fare amount, which is going to be our answer. So we're going to use those first 6 things as an input data, and we'll try to predict that output. And yeah, some things are obvious, like trip distance, and sometimes trip time will contribute it. Some probably less, but if we have that data, we should try to use it. So as previously, we take our data, we load it from the text file. In this example, in this data set, the data is already pre-divided into training set and testing set. This is a common way to do it in machine learning, that you have part of your data took aside as a testing set, usually somewhere between 10 to 30%, because when you train your algorithm, you want to also kind of test it on the data it hasn't seen yet to prevent something called overfitting. So your algorithm is so good at solving this specific data set, but will not generalize well to data it hasn't seen. It's kind of like if you want to use the analogy from real life. Let's say you get a set of questions, for example, from your teacher, and you're going to learn the only answers to those questions, but you cannot generalize the knowledge well. This is like the classic example of overfitting. You kind of want to figure out the way to solve those tasks, to be able to solve the tasks, in examples you haven't seen. And that's how we basically see if the algorithm is overfitting. So we train it on the test data, and let's run it on the training on the train data and test it on the test data, and see if the results on the test data are also kind of like at reasonable, yeah, it works well. So then on the second find, we kind of build the, we filter out the things that are not helpful for the training algorithm. Sometimes we have like trash data, or data that's like outliers, and it's going to be just confuse the model. In this case, they're just like removing the data like trips that costed $0, and also like some extremely long trip that costed like over $150, because they were they could confuse the algorithm. It's like commonly thing done when you work with data sets. The data is never perfect. You kind of try to remove things that will be either like extreme outliers or incomplete data, and so on. So this is the ML.NET also have tools for working like that, basically like some filtering, and you can also do custom filters. The second part is we're building this kind of training pipeline, and in this things we're kind of picking up different features and let know algorithms what those features are. So for example, things like payment type, rate, and type of name of vendor, we try to want to let the algorithm know that those are categories. So for example, it doesn't try to do any like mathematical transformation and for example, make some assumption that because like one vendor has ID 2 and the other one has ID 1, that other was like 2 times better because of that. So we indicate that if features that are categories, there are categories, so the algorithm doesn't try to do any math on them. And on the like kind of numerical things, we would like to do like normalization, which effectively put those values between 0 and 1. This makes the finding this kind of bottom of the cost function much more effective and much more easier mathematically. And then we can like recalculate again the proper values. So this is kind of like normalization, is like mathematical tricks that makes the calculation less complex. So there's like a lot of those things you can do to data. Those are probably the simplest one, marking the data as categorical and normalization on the numerical data. ML.NET supports a lot of them, and you know, as you work with them, you probably learn them that some of them will make the model learn quicker or give the better results. In the step 3, we build the build a training algorithm. And as I said, ML.NET is constructed in a way that you start with the what kind of problem we're solving. And by predicting the one number, taxi4, we're solving regression problem. So ML context, we pick regression, and we pick type of regression algorithm we would like to use. In this case, is the SDCA regression algorithm. There are multiple of those available. For the start, you're probably going to be confused with them, but there's also a solution to that problem I'm going to talk a bit later. But yeah, we basically append that training algorithm to the pipeline we've built at the previous step, and then we do a training in step 4. And after the training, we will get some trained model that we can start to make some predictions. But before that, we can also see a metric. So basically some data out of the training algorithm. So those are, for example, metrics provided by the ML.NET natively. So you can have value of the loss function. This is the squared loss function is the one why I was talking about earlier in the presentation. And there's, for example, R-square score that also shows you how well regression, kind of your function matches the data. 0 is bad, 1 is good, 0.7 is okay. So this gives you some kind of sense how this model could perform. And as I said, you have quite a lot of algorithms to pick and kind of type of algorithms. And as we like to do in the .NET, I like to call dot-driven development. Basically, you take an object, press a dot, and see what IntelliSense tells you. And that's where that way is supported by ML.NET. And this is an example of kind of type of algorithms you have available straight away. And then you know, you have a bunch of algorithms like SDCA on land gradient descent on or Poisson regression. So let's look at some kind of more business examples. One of the common things in retail is recommending of products that we want to give to people that basically want to upsell them, for example, when they're finalizing the transaction. And the algorithm that we're going to use is matrix factorization. In ML.NET, the kind of the input data they use is pair of products that have been bought together. And given the data set, we will be able to just, load that data and use some the matrix factorization trainer. Here we passing some options that help to work it out. Usually a lot of algorithms have decent defaults that you can start with, but then you'll want to maybe tweak with them for various reasons. And as previously, we build our, we train our model, we use it to make predictions, and then we get some kind of output data that, for example, for the product 3 and 60T, the predicted score is 0.4. Now we'll have to run kind of the matrix of all products you have with others to calculate those scores for them, and then just sort by columns and see that for product 60C, the highest put together values have like score 0.7 and so on, just do them together. Like this is the example I talked about earlier at the client, that we basically recalculated this data every weekend because it took some time, and just basically created the output in the database of the most commonly put together products for the product X. And this was working really nicely in the CI/CD pipeline, and gave really good results, and raise of sales on like 27%, because the previous recommendation engine was only recommending stuff from the similar category. But if you already bought a bike, you don't want to buy another bike. That wasn't very, very useful. This actually drastically increased their upsell possibilities, and also like 20 lines of code of machine learning plus some infrastructure built around it. So really, really good return of investment. Customer segmentation is a kind of problem that you want to maybe offer stuff to similar customers you have in your newsletter or client base and so on. So let's say with data, this is from some like winery information. Basically, like people ordered some kind of wine in different in different variety and so on. And we have those tables and the matrix that matches those customer names and so on. And this time we're using clustering, which is the algorithm doesn't use the supervision, so we don't need labeled data. And again, the steps are the same. We just basically build the model, train it, and get the output. Demand prediction. So this one example is from the bike rental, but at some clients we figure out it works really well also for figuring out like seasonal products. Most of those examples I have in practical life is from retail. Retail is really interesting area to work with this because they have a lot of data, and it's very easy to apply those things into the retail situation. So the input like from this sample from ML.NET is basically bike rental. You have some informations like, is it like a season for biking or not? Weekday, is it working day or not? What kind of weather, temperature, wind speed? It was a casual rental, so basically like kind of drop-in rental, or was it like pre-booked? And kind of the same approach. We load the data, we build our pipeline, and this is a very cool thing they done in this example. They wasn't sure which regression algorithm used, so they loaded multiple one into kind of array. and then they just for each over that array of models, and for each of them they kind of train them, and they see which one did better on metrics, and then could figure out, okay, so for us the best will be a fast tree algorithm, for example. And this brings us to AutoML, which is another interesting feature of the ML.NET. It basically automates that process. So instead of you just loading 4 or 5 algorithms into array, you do something like a regression experiment, and basically load your data in and decide how much time you want to run it. So either minutes, 10 minutes, and so on. And then ML.NET will use that time and basically try as much algorithms as it has, and also use different input parameters to the algorithms, and then just like find the best out of them. And then you can just use that best model as your trained model and build prediction on that, and then have some output that's really good or not. But you know, on some problems it works really well. And so why not go a step further, right? If we already do it like in code, so why do you even would write code at all? Because you can right-click on your project, add machine learning, you know, pick type of machine learning, load your input data, click start training, wait until it trains, and then see the results. If it looks good, just add the code to your projects. Boom, you have a working machine learning algorithm built into your project. That's interesting, but now it brings the question, should you do it? And as always, the answer is it depends. If you're working with like medical data and want to do something that will keep people alive, probably doing this with algorithms you don't know and not sure how it works and how to interpret results is not a good idea. But if you're like playing around with some pet projects, want to do some predictions, maybe you want to do some internal project to quickly prototype some stuff, then it will get you some kind of initial algorithm that you can then work on, control parameters better and so on. So it's a good starting project to basically see maybe if you can do anything with the data you already have. But as I said, step with care, because it's kind of getting into dangerous territory. So that's all for me today. I'm at Twitter at Łusiak. I'm also gonna be at Discord for a couple more hours, so feel free to hit me up. And now I'm passing the you know, the button next to the studio.